Part of B.3, compare two architectures. So we look at two register-based architectures in the previous video. Register memory architecture and the register architecture. So let's compare their advantages and disadvantages. Yeah. So let's look at one by one. Yeah. First, let's look at the register memory architecture. Yeah. Advantages. Yeah. First, data can be accessed, okay, without a separate load instruction first. Yeah. Here, so let's look at that special instruction. All right. Add R3 R1B, right? Let's recall, yeah, we had this instruction in our previous example. Yeah. So in this one, you can see for this operand, we do not need a separate load instruction. We do not need to do this load R2B, right? We do not need to do this. So it looks like we save a little bit. We save one load instruction. We save this instruction. We save a little bit. So that is the, we can treat it as an advantage from some viewpoint. Yeah. Because here, why I say this way, from some viewpoint, because later when we change our viewpoint, the same thing could become disadvantage. Yeah. Here, from this particular viewpoint, the number of instructions that we can save from this viewpoint looks like an advantage. Yeah. But wait a minute. Later, the same thing could become a disadvantage. All right. Yeah. Next, instruction for format yields good density. Yeah. Here we talk about density, code density. Another concept, code density. Yeah. Not transistor density, code. Yeah. Because here we write our programs. Our programs are translated into CPU instructions. So we look at the instructions, that density. So what's that concept, instruction density? Yeah. To do the same amount of work, for example, addition, right? Yeah. Both architectures do the same work, addition. A plus B assigned to C is assigned to C, okay? Yeah, that same thing. The number of instructions needed. So we use this code density concept to describe that. Yeah. So this one, yeah, because look at that. Because if we can save one instruction, that means we get better density. Better density. Yeah. So when we do the same amount of work, we need fewer number of instructions. That's a good thing, right? Good thing. So that's why we say good density. The other side, we need more instructions to do the same thing. So it looks like less efficient. So then we do not say good density or better density or worse density. Yeah. All right. So that's the advantage part. Disadvantage part. operands are not equivalent. Yeah, operands are not equivalent. Yeah. Still, look at this instruction. In this instruction, there are two operands. These two operands are not equivalent in this instruction. Why? Yeah. Let's look at the explanation. Since a source operand in a binary operation is destroyed. See? A source operand in a binary is destroyed. Yeah. Yeah, here, I think, this sentence is not, yeah, because if it's destroyed, yeah, because here we see two source operands, right? One from memory, one from register. That's not equivalent, right? Yeah. The one from register, we need fewer bits. From register, remember, 32, we need 5 bits. In order to represent R1, we just need 5 bits. But the memory address, we need more bits, right? Yeah, more bits. Yeah. From that understanding, they are not equivalent. Yeah. This binary operation, yeah, here, because here we're talking about binary operation, all right? Yeah. And this is not binary. This is a ternary. Ternary because there are 3. Add 3. Yeah. The binary, it is destroyed, right? The binary, so that means ADD R3B. Okay, that's the binary. So one operand is destroyed. Okay. If it's destroyed, what's the meaning of that? Yeah, here. Yeah. So let me explain this. Yeah. So this binary operation, we are talking about this instruction, ADD R3B. So that's binary. Okay, you see too. Yeah. This binary, what's the meaning of that? The meaning is, okay, one source 1, source 2. Okay, yeah. So when you do addition, the first source comes from R3. Then the second source comes from B, from memory location B. Then the result, after addition, you get a result, right? Result goes to R3. So your destination, yeah, R3, we also call the destination field. Destination field. So R3 is used in 2 different roles. At the beginning of the operation, it is used as a source operand. Then at the end of the operation, it is used as a destination field. Okay, so that's the meaning in binary operation destroyed. Yep, so definitely, so not equivalent, right? But here, even in the ternary, so this is a ternary operation, these 2 operands are also not equivalent because one, we just need 5 bits, right? The other, when we do encoding, we need much more bits. Depends on your memory space. How large is your memory space? The larger the memory space, you need to use more bits. Yeah. So that's the meaning. So you can see, one sentence, you need to explain a lot of things. There is a lot of background behind that one sentence. All right. Yeah. So let's look at next one. Yeah. here I have to erase this part because the next slide I need to use this space here. Yeah. Encoding a register number. So what's the register number? Register, that 5 bits, we call the register number. We can also call register address. Sometimes we call it register address. Register, you have address, right? Yeah. But in our textbook, it is called register number. Encoding a register number and a memory address. Yeah, that's what we just discussed before, right? Yeah. In each instruction causes variable instruction length. Yes. So here you can see that's another difference. Instruction length could be different. Why? So when you encode a register number address, 5-bit address, you need a shorter instruction, right? But if you have a memory address to be encoded inside instruction, then you need a longer instruction bits. Yeah, so look at, that's quite different. Yeah, that's a disadvantage because you use variable length instructions. In the previous video, I mentioned if you use variable length instructions, the performance will be slower. Yeah. All right. Next, CPI, clocks per instruction. CPIs vary by operand location. Yeah. So another consequence due to this kind of instruction. Yeah. CPI. Yeah. If your instruction does not have memory address inside, then CPI smaller because you do not need to go to the memory to get your data, right? But if your instruction contains a memory location, then it will be much slower because you have to go to the main memory to load the data. That usually takes much longer, much slower. Yeah. So that's another disadvantage. All right. Now let's go to the second one, register architecture. Yeah. All right. So for this one, yeah, advantages. Now you can see much better. Yeah. Fixed length instruction encoding. We can use fixed length. Okay. Yeah. Because, yeah, so you will see when we need to access data in main memory, we can do it through registers. Yeah. Later in our later discussion, we will see that details. Here, from our previous example, we cannot see that. Still, I didn't give you enough information, but in our later discussion, I will give you that information. When we talk about addressing modes, memory addressing modes, we will see that. Yeah. Because we can take advantage of shorter bits for data coming from registers. Shorter bits when we use data coming from registers, right? 5 bits, each one 5 bits. Yeah. We try to avoid using memory address long bits directly in our instruction. So in that way, that we will span a lot of long bits. So if we can avoid that, then we can get fixed length instruction encoding. Yeah. So we can do that, but you need more information to understand that. At this point, you may not be able to understand this probably completely, yeah, because we have a lot of story behind it. Yeah, we need to learn in our next video. Yeah, not next video, next part C. Yeah. All right, simple code generation model. Simple, yeah, relatively simpler, right? It is simplified. Okay, fixed length. First, fixed length simpler, right? Simpler than the variable length. So then, smaller number of addressing modes also make it simpler, right? So a lot of things you can make this architecture simpler. Yeah, simple code generation model. Yeah. Then, instructions take similar number of clocks to execute. CPI, the difference is not that big. Yeah. The difference is not that big. So similar number of clocks to execute. Yeah. All right. Yeah. But this property, yeah. When we learn more and more, we won't have this property anymore. Yeah. Because the CPI change will be different, not similar. For example, here, let me give you a simple example. Addition and multiplication. You have addition instruction. You have multiplication instruction. When you do addition, it is very fast. When you do multiplication, it is very slow. How can you have similar number of clocks to execute addition instruction and a multiplication instruction? Right? Impossible. Okay? Yeah. So later, so we will see 1 to 10 ratio, addition versus multiplication, but for the floating point. Integer will be faster, but for the floating point, addition and multiplication, the ratio is 1 to 10. So you cannot say similar number of clocks to execute. Yeah. So this part, not quite right. Yeah. Not quite right. Yeah. All right. Disadvantages. Yeah. Higher instruction count than architectures with memory referencing instructions. Yeah. In our previous example, we need one more instruction, right? Do one simple addition. The first one we use 3, and this one we use 4. One more than that. So higher instruction count. That's we can treat as disadvantage. Yeah. But for the long run, it's not a disadvantage. For the short run, it is a disadvantage. But for the long run, actually, it becomes an advantage. Yeah. Yeah. All right. More instructions and a lower instruction density lead to larger programs. Yeah. Because when you do the same thing, you need more instructions, right? Larger, longer instruction sequence. Yeah. So that's the disadvantage. But why I say for the long run, it's not a disadvantage, because the overall performance will be faster. So for this one, the overall performance will be faster. So why? You will see it reduced the number of memory trips. Yeah. So long run will be faster. Why? The reason, reduce the number of memory trips. Memory trips are very expensive. It usually takes a long time to get data from memory. Why this will reduce number of memory trips. Very simple. Okay, if we look at the whole program, think about if one piece of data is used multiple times, because we just loaded once and put it in a register, next time when we need to use it, the same data piece, we just reuse it. We get it from the register. We don't get it from the memory another time, right? In this one, in this case, the next time when you need to use the same data piece, you may need another trip in from memory. That will be more expensive, slower. Yeah, so that's the reason. Okay, yeah, later we will see that kind of thing more. Yeah, all right, so let me stop our video B.3 right here.